Welcome back to another deep dive. You've probably heard of black holes, right? Those
Yeah.
cosmic devourers. But what if there was their exact opposite? Today, we're getting into the really mind-bending world of white holes.
Yeah, and our mission today is to unpack what a white hole actually is. We've looked at your sources from the, foundational physics papers right up to the latest quantum theories. We want to figure out why they're still so speculative, even though Einstein's equations technically allow them, and what they might tell us about some big cosmic mysteries.
Okay, so the exact opposite of a black hole. How do physicists even start to define something that sounds so, well, counterintuitive?
Well, what's really key here is their main feature. It's like a boundary of no admission. Think of it as a cosmic one-way exit door. Matter, energy, light, information, it can all escape from a white hole. But absolutely nothing can cross its event horizon, that point of no return, to get in from the outside.
So completely the reverse of a black hole where everything goes in and nothing comes out.
Exactly. It's not really anti-gravity, more like the flow of space-time itself is just flipped, heading outwards.
Right. From black holes, we actually understand those fairly well, don't we?
Yeah.
They form when massive stars collapse. We've got loads of observational evidence, things like gravitational lensing where light bends around them, and those super hot accretion disks of gas swirling in.
Yeah.
They're definitely real. So why aren't white holes just as real? What's the holdup?
Yeah, that's the core issue. Classical white holes, the original idea, they face some pretty big hurdles. First, unlike black holes, there's just no known astrophysical process, nothing we observe that would naturally create one. Stars collapsing, that makes black holes. Nothing seems to make white holes.
Okay, no formation mechanism. What else?
Second, they're predicted to be incredibly unstable. Like ridiculously so. Even a tiny bit of stray matter falling towards a white hole could potentially cause it to just collapse instantly into a black hole.
Huh. So they wouldn't last long, even if they did form somehow.
Precisely. And third, there's a thermodynamics problem. Their constant spitting out of matter and energy seems like it would violate the second law of thermodynamics.
The entropy law.
Yeah.
Things tend towards disorder, right? And a white hole sounds like it's doing the opposite locally.
Kind of, yeah. It appears to decrease entropy in its vicinity by expelling organized matter energy, which is generally a no-no.
Okay, so unstable, no known way to form, potential physics law violation. It sounds like they should just be a mathematical curiosity. So why are physicists still talking about them? What keeps the idea alive?
This is where it gets really fascinating. It ties into one of the biggest puzzles in modern physics, the black hole information paradox.
Right, the problem of what happens to information that falls into a black hole, especially if the black hole evaporates later. Quantum mechanics says information can't just vanish.
Exactly. If it's destroyed, quantum mechanics breaks down. So theorists started looking for ways out. And this led to the quantum bounce idea. Some modern theories, especially loop quantum gravity, which tries to merge quantum mechanics and general relativity, suggest maybe black holes don't have that infinite singularity at the center. Instead, when things get incredibly dense, down at the Planck scale, the smallest possible scale, maybe the collapse halts and bounces.
Bounces, you mean?
It transforms. The black hole effectively turns into a white hole, very briefly, and ejects all the information that ever fell in.
Whoa, so the information isn't lost, it just comes back out later.
Yes, but in a, let's say, highly scrambled, almost unrecognizable form. It preserves the information principle, avoids the singularity, and provides a physical mechanism, albeit a quantum one.
But you mentioned briefly, if it's so quick, why haven't we seen this?
That's the time dilation kicker. Because of the intense gravity, while the bounce itself might only take milliseconds in the black hole's frame of reference. For us, watching from far away, that process would appear stretched out over potentially billions, even trillions of years for a large black hole.
Longer than the age of the universe.
For big enough black holes, yes. So that could explain why we haven't just seen black holes popping into white holes all over the place. It's happening on an impossibly long time scale for us.
Okay, that's a wild thought. So connecting this to the bigger cosmic picture, where else do these ideas lead?
Well, it gets even grander. Some people have speculatively suggested the Big Bang itself might have behaved like a kind of gigantic white hole.
The origin of everything is an ejection event.
Sort of, yeah. Sometimes called the small bang hypothesis. All matter and energy erupting outwards from an initial point. It's highly speculative, of course. And then there's the connection to wormholes, theoretical tunnels through space-time. In some models, if wormholes exist, a black hole could be the entrance and a white hole could be the exit door.
Connecting different parts of the universe. Or even different universes.
Potentially. Though, again, super speculative, These ideas often need things like exotic matter with weird properties to hold the wormhole open, stuff we've never seen.
Right, so this is deep into theoretical territory. What about really, finding one? Is there any hope of observing something like this?
Well, direct evidence? No, not currently. We haven't pointed at a telescope and said, aha, white hole.
Hmm.
But scientists are thinking about possible indirect signs, fingerprints they might leave behind.
Like what?
There are some really out there ideas, like maybe certain types of gamma ray bursts that happen without a supernova explosion could be a sign. Very speculative. More promising, maybe, are future space-based gravitational wave detectors like LISA. They might be sensitive enough to pick up faint, unique signals from white hole events in the overall background hum of gravitational waves, the stochastic background.
You get gravitational waves.
Yeah.
Anything else?
Possibly the cosmic microwave background radiation, the CMB, specifically subtle patterns in its polarization called B modes. Some models suggest decaying white holes could leave a very specific imprint there. The dream scenario would be multi-messenger astronomy, seeing hints in both gravitational waves and the CMB, maybe correlated in some way across cosmic time. That would be really compelling evidence.
So it seems white holes are still very much on the theoretical drawing board, but the potential payoff for understanding them seems huge.
Absolutely. They remain, firmly in theory land for now, but their mathematical basis is sound within general relativity, and they offer potential solutions to really deep problems like the information paradox. That makes them incredibly compelling to study.
It feels like even if they don't exist exactly as first imagined, chasing the idea pushes physics forward.
Exactly. The study of white holes, however speculative, is vital. It's not just about asking what are they, it's about what they force us to confront about quantum gravity, space-time information. It pushes us to explore the